Hello, everyone. My name is Drgona. I'm a data scientist at Pacific Northwest National Laboratory, and today I will show you how we are using differentiable optimization as a lingua franca for scientific machine learning. Scientific machine learning is a combination of machine learning with classical scientific computing, and there is a need for improving computational efficiency and scalability of these heterogeneous scientific simulations that are ubiquitous to many areas of decision-making and scientific discovery. In our team, we set ambitious objectives to develop domain-agnostic software and algorithmic framework that can support this new scientific computing, enhanced with data science and high-performance computing. But before we embark on this journey, we need to review how we are doing optimization today. In classical constraint optimization frameworks, we are formulating objective functions, equalities, inequality constraints with fixed parameters, and we are solving them online with a given set of parameters that can be represented by initial or boundary value conditions. And depending on the problem type, we are using solvers such as imperial point or active set method to give us solution. This approach can give us hard constraint guarantees, but typically it's computationally demanding in real time when we need to repeat the optimization and again, let's say in dynamic optimization setting, with every set of new measurements. Parametric programming, on the other hand, is a nice conceptual idea that aims to alleviate this online computation complexity by pre-computing the solution of optimization problem offline and representing the solution as a parametric solution map that maps the parameters to decision variables. Unfortunately, classical multi-parametric programming solvers, they don't scale to practical or relevant problems. So what can we do? Recently, people have been using machine learning to help us with the scalability issues of constraint optimization problems. In particular, people propose to use imitation learning on labeled data set of parameters and decision variables obtained by computing a distribution of online optimization problems with iterative solvers such as imperial point, and to use machine learning algorithms such as deep neural networks for regression or classification tasks to obtain this approximate solution map of parameters to decision variables. This is scalable, but requires the original solver to begin with. And this can be quite computationally demanding to generate all the training data. On the other hand, reinforcement learning doesn't really require original solver, but it's interested in problems where there is some temporal dimension. So we have some dynamic system environment that can be a real physical system or computational model. And we learn the parameters of the actor that perturbs the system and the parameters of the critic, which observes the states and rewards from the system environment. Then we can now use automatic differentiation to compute the sensitivities of the actor critic to obtain the policy gradients. In deep reinforcement learning, these both actor and critic are represented by black box neural networks. This is flexible and can be scalable, but classically can handle hard constraints, and we require a lot of samples to converge. So natural idea in the domain of constraint optimization and machine learning is how can we bring the benefits of both hard constraint guarantees for classical solvers and flexibility and scalability of machine learning methods. To achieve that, we propose differentiable parametric programming as a unifying approach to data-driven optimization that is based on automatic differentiation. And we really see differentiable parametric programming as a generalization of successful physics-informed neural networks. In our formulation, we start with some nonlinear objective with primal decision variables x and parameter xi that needs to satisfy some set of equality and inequality constraints. And we are searching for a solution map that is parameterized by theta that maps our parameters to decision variables, as opposed to just solving directly for decision variables as we would be doing in the direct online optimization. Okay, how can we solve this with gradient-based optimization using automatic differentiation? Is to use the Lagrangian formulation. trick that is being used by many constraint optimization solvers. And it constitutes using our constraints as residuals or penalties in the objective function to give us the gradients of the direction of the descent. In the simplest form, we can use penalty functions that are simple two norms with some weighted factors, or we can go for more advanced approaches like barrier functions or augmented Lagrangians that can update our dual variables in the problem. But really the bottom line here is by reformulating the sampled parametric programming problem into Lagrangian form, we can now employ automatic differentiation to compute the sensitivities for gradient-based optimization. This has been done in many areas of scientific computing, but until today, it has been very tedious to implement them in machine learning frameworks. Everything needs to be done from scratch. To alleviate this problem, in our team, we are developing NeuroMancer toolbox that stands for neural modules with adaptive nonlinear constraints and efficient regularizations as a mouthful. It's essentially a Python-based toolbox that comes up with these high levels of abstractions and operator overload to provide you with user-friendly and minimalistic API for formulating parametric programming problems with constraints and solving them using automatic differentiation. So how can we map the mathematical formulation right inside into the code? It's shown on this story example. And we take inspiration from algebraic languages such as Jump in Julia, CDXPy, or PyAmo in Python, and YAML in MATLAB that are based on defining the problem as abstract symbolic variables that can represent your decisions or sample parameters. And we introduce range of neural network architectures. We implement this operator overload that allows us to formulate this algebraic language, define new variables through these polynomial expressions that we can directly minimize as our objective term or impose some kind of equality and equality constraints. And we aggregate everything together through selected Lagrangian reformulation that is used in our constraint optimization problem construction. So it is automatically generated by framework. We have differentiable constraint problem as a PyTorch model that can now be used with standard gradient-based solvers that are available in the framework. Okay, so what it allows us to do is to solve non-convex constraint nonlinear programs at scale. Why? Because we represent constraint optimization problem as a computational graph, so you can really think of it as a domain-aware neural architecture. We use high-performance computing GPUs to solve this problem offline, and then we obtain online solution that is based only on evaluating the trained solution map, which is orders of magnitude faster compared to solving the optimization in real time with iterative solvers such as Interior Foil. And we can go beyond static constraint optimization problems. In our work, we introduce what we call differentiable predictive control. That is essentially constraint model-based policy optimization to solve parametric optimal control problems. How do we do so? This is very high-level abstract computational graph. We have some distribution of our control parameters, such as initial and boundary conditions. We have control policy, which is neural network, as in reinforcement learning. But opposed to model-free reinforcement learning, we represent our value functions by system dynamics model that can be neural differential equations or stage-based models, and model-based model predictive control objective functions, such as reference tracking, constraint penalties, all the terms in the Lagrangian that can be domain aware. And we differentiate this with automatic differentiation to compute the gradients of the policy. Does it work? Yes. Here is a hello world example in control theory. Let's have an unstable linear system, and let's stabilize this system to the origin, given state and input constraints using differential programming. Here we show this simple example that can be trained with relatively low computational requirements. The advantage of having model-based terms is that the convergence is very faster. We are able to solve this particular problem within hundreds of epochs. It doesn't require expensive computing. This was solved on CPU under 1 minute of offline training. And we can see like the control trajectory is nicely stabilized, the stay within the constraints, and the policy does its job in terms of performance and safety. We can go even beyond that. We can introduce uncertainties in the system dynamics that can be represented by linear state-space models, nonlinear state-space models, neural differential equations, or standard differential equations if we have white box systems. And we are able to solve stabilization of stochastic systems, stochastic obstacle avoidance given nonlinear objective quantities and nonlinear constraints. To go beyond these academic examples, we have shown a range of applications in building control and power systems, and here I'm showing just one to highlight the potential of differential programming on dynamics error economic dispatch problem, where we start with trajectories of power system networks generated by studying differential algebraic equations in PNNL. And we learn domain-aware Huffman model to act as a surrogate for these differential algebraic equations. Is very expensive to solve. And now when we have this data-driven system ID model, we plug it together with the control policy, obtain a closed dynamic system, impose control objective, and differentiate this problem to learn explicit control law fully offline by using PyTorch optimizers. This allows us to obtain 5 orders of magnitude speed up compared to real-time optimization using intelligent point. This is fantastic because this is a difference between being able to solve this problem in real time or not. And we have shown that we are able to scale this with minimum loss in solution quality, where on the right-hand side figure, the dashed lines are the solutions obtained by our method, and solid lines are integral point solutions. As a conclusion, in our team, we are working on systematic combination of scientific computing with machine learning in domain agnostic algorithmic and software framework, which we call Neuromancer, that combines differential programming with parametric programming, sensitivity analysis, constraint optimization solvers, and dynamical system modeling and control in one software package that can be readily used for research purposes. We are exploring other avenues such as more advanced constraint optimization solvers for machine learning models, integrating latest state-of-the-art architectures, doing some uncertainty quantification, and our long-term vision is really to solve difficult problems in scientific discovery and solving large-scale non-convex decision-making problems in engineering. Thank you very much for your attention, and if you are interested in our work, please check out our open source repositories.